Physics 2211 Lab 5, Choose Your Own Adventure. The purpose of this lab is to evaluate the effects of drag and gravitational forces on an object's motion after being dropped from rest. I'll use Tracker to track the observed motion and then GlowScript to develop the computational model to graph the system's motion. And a sneak peek of the results, based on the similarity of the observed and predicted graphs of motion, the Slinky's motion was affected by both the drag and gravitational forces. So the fundamental physics principles that are used in this lab are Newton's second law, which derives net force to be the change in momentum over the change in time, which equals 0 in this case since the tension force and gravitational forces cancel each other out in opposite directions, as well as the velocity update and position update formulas that can be derived from N2L. And then also another physics principle is drag force, which is a resistive force that opposes the motion of an object through a fluid, the fluid being air in this case, and that's equal to negative b times the absolute value of velocity squared, where b is a drag proportionality constant. So the tracker setup, we have the system being the Slinky and the surroundings being the Earth. The initial conditions are that the mass equals 0.200 kilograms. The initial position is this x value, which doesn't really matter. But then we have the negative 1.205 meters as the starting initial position. The initial velocity is 0 in all components. The length of the Slinky is approximated to be 1.2 meters based on the guy's height and using a calibration stick. And the drag proportionality constant is 35 in this case. So here's a video showing the tracker recording footage. Okay, so on to the next part, GlowScript. We have the initial conditions on the left here. And then for the first part, while t is less than 5.5, this is where the spring has not compressed and is moving as a unit yet. It's when the tension force and the gravitational force counteract each other. So then we have the force updates with the F net equaling the weight plus the tension force. But then in the second part, while t is greater than or equal to 5.5 but less than 7.83, now since the the Slinky is traveling as a unit, we now know that there's no tension force but rather drag force that counteracts the weight. So now the net force will be the weight plus the drag force. And then the same position update and velocity update formulas. So the results, so here are the results. You can see on the right here, obviously both of them will have the predicted and observed graphs of motion will have the same position, y position, until the 5.5 seconds, and then they will start to deviate. So we can see here that more closely that the observed motion is slightly higher than the predicted motion's y value. And potential sources of error for this are that there could be unaccounted for external forces that are making the observed motion be slightly higher than the predicted motion. And there's also tracker placement inaccuracy on my hand because I don't have robot precision to place the point of mass at every instance. So extra questions, what if and what else? So does the bottom of your model Slinky stay stationary just like in the video? Yes, until the top of the Slinky reaches the bottom of the Slinky, since the net force cancels out and becomes 0 because the tension and weight are equal in opposite directions. And how is the Slinky's motion affected if it has a larger mass? The general answer would be that it depends on the magnitude of tension, since the net force will be 0 if the tension and gravitational forces balance each other out. So the mass doesn't affect it unless the tension and gravitational forces equals a net force that is non-zero. Okay, thank you.